So today we are going to start our study of functional programming. And we have, of course, to have a language that will support functional programming. And functional programming is a rather old idea. Actually, it started in 1960s when the first list processing language was developed, and that is Lisp. Lisp is list processing language, and this language was developed by John McCarthy and was first used with an IBM computer, IBM 709, an old IBM machine. So the idea of that language was that everything should be a list. And list is a rather powerful concept. And we've seen, of course, lists in Prolog. And let us start by saying that Lisp was evolving into first language for research in artificial intelligence. After that, Lisp was used in variety of ways. And then came one an idea to somehow purify Lisp and to take from Lisp only those things that are essentially very important and to make one purified, reduced version of the first class language. That was Scheme. Scheme has plenty of interpreters because it is used as a first programming language in many schools. And then Lisp and Scheme somehow was developed at MIT, primarily where it was used as a first programming language, and in many other schools. So you have plenty of these Scheme interpreters that you can use. Scheme is first-class language. First-class language means that satisfies something like 10 rather strict conditions that have to be satisfied. You're going to see them today. And then what happened next is that Scheme was used by a group of people who made one language system called Dr. Scheme. Well, Dr. Scheme was a nice language, and it was used for substantial time. And then after that, they kept adding new features to that language. And then one day they said, this is no longer going to be called Scheme. It is going to be called Racket. Why Racket? They said, we have no idea, but it is a good word. We like it. So they started to call it Racket. And then Racket, step by step, evolved into something that you will see when you go to their website as a new paradigm. They say that this is the paradigm of language-oriented programming. That means when you want to solve a class of problems, you develop new language. The first language that they developed using Racket was, of course, Prolog. And you can see it at the beginning of their website. It is ancestor problem written there. If you went to download that, you've seen it. So they think that in the future, people will develop new languages when they want to solve a class of programs or problems, and that is the mission of Racket. Now, is this going to happen or not? Nobody knows, and we have to wait to see the evolvement. But Racket has as its core Scheme. So to use Scheme, we can use Racket language processor and to see how it works. And so since we have a new toy, let us play with a new toy. So the most important thing in list processing is a list. So how to make a list? You open parentheses, put here an operator, and then operators, for example, when I make this list where I have operator plus, and I have 1, 2, 3, 4, I want to apply this operator to these operands. So the idea of functional programming is that the basic data object is a list. List is written by putting left parenthesis, putting at the top of the list as a head an operator, and then you have here operands, operand 1, operand 2, operand 3, operand 4, any number of them. And then you close the list. Now, if you have this kind of list, it is a function. Function where this is the operator and these are operands. Each function is returning a value. So when I press return, I get the sum 1 plus 2 plus 3 plus 4 is 10. And this is the result of that list. So you can say, okay, so this is the basic data structure, list that contains operator and operands and enters the value. Of course, in functional programming, everything is a function and everything returns a value, including if statement. So I can also try to see how this works. Is it working with 3 arguments? Yes, it is. 1 plus 2 plus 3 is 6. Okay. So we go here to see, is it working with 2 arguments? So when we play with this toy, we are going to see how it works. 1 plus 2 is 3. Excellent. Can you do it with 1 argument? Plus 1. Result is 1. Well, I can say, okay, let me see, is it capable of working without arguments? Okay, press return and get 0. So you say, aha, what is 0? 0 is obviously neutral element for the operation of addition. So I can do the same thing and say, okay, let me see, is it working with multiplication? 1, 2, 3, 4, 5. So we want to multiply 1 times 2 times 3 times 4 times 5. What is this? 5 factorials. 5 factorials is 120. So we press return and we get in this dialog 120 as the result. So it works this way. If I reduce this to, for example, 2 arguments, 1 times 2 is going to be 2. And then going back to previous example, go to see how it works with 1. So multiply 1. Well, this looks a little bit strange, but you get 1. Okay, so we can try also to multiply without arguments. What's going to happen now? Well, press return and see comes 1. So 1 means that this is neutral element for operation of multiplication, same as this 0 used to be neutral element for operation of addition. Now, you can say, okay, I have addition and subtraction. Maybe I should try to see how it works with division, how to divide things. So let us say division, and let us divide 1 and 3. That's usual test how this works. It gives you rational number, 1 over 3. So it can work with rational numbers, nice thing. So if I go back and say, let me divide this by 3, that is real value, that has mantissa and exponent. So what happens in procedural languages when you divide something that is integer and something that is real number? Obviously, they are all converted to real numbers. They are divided, and after using real numbers, you get what? The result written as a real number. How many digits we have here? 16. Aha, 16 digits. That means this is mantissa and exponent of real numbers in double precision. So it is using 32 plus 32, 64-bit values for this division. So you can also try to see whether it wants to divide some value, for example, 3, like this. Is it working as reciprocal? Yes, it is. It is dividing 1 divided by 3. And if we go here and do this with integers, you get 1 divided by 3. So you can be tempted to say, aha, neutral element for this would be 1. So you try that, but you get the arity mismatch. It says the expected number of arguments does not match the given number. So it has to have either 1 or 2 arguments. So it said expected at least 1 argument, but given 0. So in this case, this is not working. You can also try to see what happens with subtraction, and the same situation happens with subtraction. So you can say, let us subtract 1, 2, 3. What's going to be the result here? Well, it is going to be -4, because this is 1, -2, -3. -2 minus 3 is -5, plus 1 is -4. So this is how these things work. Let me ask you something immediately. Is this font of letters sufficient or too small? Can you see this comfortably on your screen, or you need bigger letters or something else?
That's good.
Is good? Is readable?
Yes.
Okay, thank you, sir. So another thing that you always try to see when you see something new, can you multiply some numbers? And what is uh, the big value that will come out of this? So I want to multiply now these numbers that you see here. And when I press return, I get the result. The result has, as you see here, around 50 digits. And therefore, we learned one new thing, that integers are not limited. They don't have limit. They have uh, an arbitrary number of digits. So that is the property of scheme. Scheme and Lisp and Racket, all of them deal with integers as strings of digits, and you can have any number of them. So you can have large numbers without any problem. Okay. Now, uh, this is how we play with numbers and with digits. You will find that all objects are dynamic objects that we have here. So I can define an object if you want. So you have to say the word define. Define. So let us define f. And this f is the value 1. So we defined f, and we gave the value 1 to it. So scheme is saying nothing. When I say, give me this f, it is going to say f is 1. Okay. So we can say now set, which is a kind of assignment. Set f to be 13, for example. Again, nothing happens. But if you want to see what is f now, so when I say f, means give me the value of f. F is now 13. So is this an integer? Yes, it is. May I try to change this and to change to another operation? Well, I can try to say set f, for example, to be operator plus. How about that? Is this going to work? So now I ask, what is now f? It says procedure. Now f became a function. Well, if it is function, then I'm going to apply it f to 1, 2, 3. What happens now? 1 plus 2 plus 3 is 6. So as you see here, f used to be 1. After that, with this set, we changed this f to 13, and it was 13. And then we said, now you are going to become a function, addition. And it say, yeah, f is now procedure plus. I apply this function to 1, 2, 3, and get 6. So this f is the name for an object. And this object can be whatever I want, including function. So it is possible to redefine this f. You can say define function. Now, since in all lists you have the name of function and the value of argument, so this is function f applied to argument n. What we are going to do there? Well, we are going to multiply n times n. So this is going to be the quadratic function. So I defined f of n, which is n times n. To see what is going to happen now. Well, it is definition of function. I ask what is now function f. It says procedure. Okay, procedure f. Let me see how this procedure f works. If I apply this procedure to argument 5. So what's going to happen? Function is this function. N is argument, okay? And then I apply this function to this argument 5. So 5 is going to jump inside as the argument, and the function will multiply 5 times 5. So when I press enter, it is going to give me 25, which is the result of this operation. Okay, so you see how simple it is to define function. So let us now see other ways how to define function. One which is important way is to say I'm going to define f. I'm going to define f to be a function, and this function is going to be defined as a general function that has the name lambda. Lambda of n is, let us say, n times n, like this. Okay? So we now say we are redefining this function, and this function has this form. It is function that has name lambda and has argument n, and then is multiplying n times n. So when I do that and apply that to 5, I get again 25. So this f that we have here is now a procedure. This procedure has this value here. So the question is, what kind of animal is this lambda? Well, this lambda is function that is anonymous. It doesn't have name. So if I say like this, lambda, this is the function that is processing its argument. It is anonymous function, function without name. All of them are called lambda. I can change this in a variety of ways, and it is always going to be lambda. So if I apply this function to argument 5, I'm going to get 25. So I have function that I define here and apply it to this 5, and then get that this function works like this. Now, scheme, same as Lisp and same as Racket, is an ultimate procedural language. So I can define a variety of functions in this way. For example, I can come and say define function of multiple variables. So let us take Pythagoras theorem, A and B, and we want to compute the C of that. So this Pythagoras of AB is going to be square root. Is square root working? Yes, it is working as the same thing as, so we now have to say A squared plus B squared. Now, the only thing that you have to learn is to put operators before operands. So I have to compute A squared, which is A times A, and this is plus, b times b. So we have to put here multiplication and bb. Okay, like this. So what I have now, I'm defining function Pythagoras of ab, and I'm computing a squared plus b squared. Here is a squared, here is b squared, here is plus. One thing that we've seen from the very beginning, that space is the part of this language. So space is the part of scheme because I don't have other separators other than spaces. Therefore, if you don't put space between this multiplication and a, scheme will misunderstood this to be the argument asterisk a. So you have to put these things properly. So now if I say, give me Pythagoras of 3 and 4, so 3 is going to replace A, 4 is going to replace B, and then you are going to compute A squared plus B squared, and 3, 4, and 5 are the Pythagoras theorem, obviously. So this all works very nice. You can also say something more complex. For example, define factorial function. How to define factorial function? You can say define again, and then we are going to take our function f and redefine this to be factorial f of n. So how to write factorial function? Well, this is simple. If we have that n is less than 2, so n is less than 2, which means if n is 1 or n is 0, what has to be returned? It has to be returned 1. Okay. What has to be returned for our other values of n? How to make factorial of that? Well, you multiply n times function of n minus 1. So we are going to multiply n with function f of what? N minus 1. So we have to put minus n and 1. Okay. Is this okay? N minus 1. This is now a factorial function. We can ask what is factorial of, for example, 5. That's what we had at the beginning. Factorial of 5 has to be 120. So you see here, in this single line, we have a definition of a recursive function. I'm defining f of argument n, and this is an if statement. An if statement that has here condition n is less than 2. If f is less than 2, for example, I come here and say, give me factorial of 0. It is 1. Of course, that's what we have written here, that factorial for n less than 2 has to be 1. If n is greater than 2 or 2, then we are going to take multiply n and this factorial f of n minus 1. So this f is now a recursive function. It is written in a single line like this. Very clean, very elegant, very readable. Once you learn to put this in front, this is just a trivial thing. Okay. Now, also, you can ask what is factorial of, for example, some big number, factorial of, let us say, 10. What's going to happen now? It is this 3 million. Okay. The next, what I always wanted to know, what is the factorial of 100? Is this here? So this works. What is the factorial of 1000? Here it is. Okay. So do you see a little bit the flavor of this language? This is like a new toy. So we played with it, and it is a nice toy. So this is a little bit of the spirit of functional programming. You have here operator, and you have operand. Apply operator to operand, and what you get as the result, you get the result. And the result is this, what we have here on the screen. You can also define lists that have nothing but objects inside. So let us say this is a list. So this is symbolic way to define list. And the echo is going to be, this is a list. You can also say define this as a list. So you can say uh, define this, and let us call it L, capital L. Okay, this is a list. So we now defined this list. If we ask, show me what is L, L is going to be the list. Now, we can ask also, what is the head of this list? So head is called car of this L. And unsurprisingly, you are going to get the value this. Nobody is asking, but logically, you could ask why I need this apostrophe here, this quote. This is called quoted list, because if I don't put that, this word this is going to be used as an operator, and these are going to be operands. So if I define this list without this quote, so go here and remove this quote, what's going to happen? It is going to create an error because this word this is just a symbol. And this is not an operator and cannot perform any operation like this. So use of a class keyword is not in a class. So it is not an operator. So you are expecting to have an operator, and this is not an operator. However, same way as we have a car, which is head of list, we can have also CUDR. CDR is the tail of list, okay? And it tells you is a list. This is the tail of this list that has 1, 2, 3, 4 components. You have head and tail. Once you have head and tail, you can also have recursive functions. You can decompose that like in Prolog and do whatever you want. So you can also define, if you dislike this car encoder, you can say define head, head to be car. So what is now this head? This head is now procedure. If I ask what is, oops, head, it is going to say it is procedure hard. So I can say, give me head of list L, and it is going to give you this. We can also say define tail. Define tail to be CDR, which is pronounced CUDR. Now, why these strange names, car and CUDR, which are having no meaning at all? Well, for sentimental purposes. For sentimental purposes, because in 1960s, this was contents of address register of this old IBM computer. And this CDR was contents of data register. So they were manipulating contents of address register and contents of data register. And obviously, this has no meaning with head and tail at all. But from that moment on, everybody said, well, this is our trademark. We don't want to forget our car and CUDR. And therefore, they remained like this. So if you want to say, give me tail, so I'm now redefining this tail of this list L, it is going to give you is a list as it should be. So you have lists, you have operations, you have functions, you have control structures like if, you have everything that you might wish to have. And this beauty is called scheme. Okay? Now you know everything and we can have exam on Wednesday. Of course not. What are we going to do now? We will try to study this language in some careful, organized way. So let me try to see, do I have something to share with you? And this is this here. Uh, do you see 600 part 4? Scheme and functional programming. Is visible or not? Can somebody say yes or no?
Yeah, it's visible.
Okay, thank you, sir. Okay, so part 4 of this course is functional programming or scheme. And we have variety of programming paradigms: procedural, non-procedural, logic programming, functional programming, and object-oriented programming. So now we are at this degree, at the level 4 of our 5 degrees. After that, we are going to go to study object-oriented programming. So functional programming is subset of declarative programming, and we have many languages that support multiple paradigms. For example, C++ supports procedural and object-oriented paradigm. Scheme supports procedural and functional paradigms. And imperative versus declarative, of course, imperative languages are specifying what computation has to perform step by step, and declarative programming specify what the program should accomplish without giving control flow and algorithmic steps. So when we defined factorial a minute ago, obviously we could do that in various ways, but this was a declarative way of specifying factorials. One thing that functional programming dislikes very much are side effects. Side effects are something that happens in addition to function that returns a value. So pure functional programming wants to have everything as functions, and each function has to return a value. Each expression has to return a value. Therefore, the goal of functional programming is to eliminate or minimize side effects. So imperative programming uses side effects to produce program results. So when you say A equals B plus C, you are practically computing B plus C. You are putting that in A, this is a side effect, and then you return that value that nobody uses. So you can say in C++, C out, and then insert open parentheses, say C equals A plus B. So A plus B is computed, it is stored in C, that returns the value of C, then you insert this value in output stream, and then it appears on your screen. So side effects are not safe way of programming, and that is one of reasons why we have this kind of programming that we mentioned earlier. So if you have this function cube, I have here that it returns an integer and it is having an argument x. So what I'm returning here? I'm returning x times x times x, and this is cube. That's perfectly okay. However, I'm also having one uh, side effect. I say take this value g and decrement it by x. So this is some global variable that I'm changing, and this is side effect. Side effect is doing anything except what is returning by a function. So this ugly side effect here has this consequence. If you say multiply cube of 2 and cube of g, you're going to get different result than if you multiply cube of g times cube of 2. So side effects are killing the commutativity of multiplication in this example. So of course, this is example that is constructed to show dangerous form of side effects. But generally, side effects are not particularly desirable unless you know exactly what you are doing. So another thing are mutable versus immutable objects. Uh, Obviously, we would like to have mutable objects, which are objects which can be modified after they are created. So you can change their state. An immutable object is object whose state cannot be modified after it is created. That means it has the value as it is. For example, you say pi equals 3.14, it stays all time. There are advantages of immutable objects. No need to copy them. Uh, because these objects can be huge, huge blocks of memory. So if you have a pointer that you use to access that object, this is a good thing. So all object-oriented languages like Python or Ruby or Java access objects using references. You have object that is a piece of memory that contains data and pointer to the beginning of that. And you say, this is the object, but you are not having the possibility, easy possibility to copy that object. You say, we don't want to copy, we don't want to mutate that object. It is immutable. It is staying in memory. We access it and we copy only pointers. So some languages support both mutable and immutable objects, and this is what we have in Scheme. One of fundamental programming paradigms is functional programming. So programming is organized as evaluation of functions. Try to avoid mutable objects, avoiding states and changes of states, and avoiding side effects. So function output depends only on arguments and not on state. So f of x always returns the same value for x. Of course, there is also mathematical background of this, which is called lambda calculus. And lambda calculus is a formal system of investigating function definitions, applications, and recursion. And again, mathematically trying to find what is the most elementary operation from which we can start. The use of unnamed anonymous functions without side effects is one of important things. So like lambda. Lambda is function that performs some operation, doesn't have any name. It is an operator without name that operates. The essence of operation is preserved without telling what is the name of it. Name can be whatever you want. So functions that accept arguments and return as results other functions. This is going to be something completely new. So we are going to have functions that can return another function. You don't have something like that in any of of languages that don't support functional programming. There is no possibility to return a function from another function in C++ or in Java or in C. You can return the value, but not the function itself, the whole procedure. This is possible here. Lisp was invented by John McCarthy. Here is John McCarthy. And first implementation was on this IBM computer in late 1950s. So first was Fortran in 1957, and then in 58 was Lisp. And then after that, it was evolving, developing, and it is still alive. Still alive is Fortran, used by engineers every day. It is used also as Lisp, as industrial language, but it has plenty of things that people filled inside in addition to this Scheme core. So Lisp is a family of languages. You have so-called Common Lisp, which is industrial strength general purpose language. Scheme is minimalistic approach to purified functional programming. And Dr. Scheme is initial non-standard expansion of Scheme and then expanded to Racket. And then it is computational environment that is used for general purpose programming. So There are many implementations of Scheme and Common Lisp. You can find them on internet. You can go and download Scheme from, let us say, MIT. You will find there are something like 7, 8 of them that are currently on internet, and each of them has some specific properties. Some have nice, shiny integrated development system. That Racket has the same thing. And you will use most likely not this interpreter that I used, but the Dr. Racket, which is something that has 2 windows and has 1 window for definition of functions and the other for execution. So this is very nice. All this is available. Both Scheme and Common Lisp have language standards. So this is not the case with Racket. Racket is a live language that is modified, and each year you have something new inside. However, Scheme and Common Lisp are standardized using ANSI standard. American National Standard Institute has standards for this language, and we have them. Main characteristics are main data structure is linked list, and everything is based on lists. So notation is that you have operator, operand, operand, so you have function and arguments here. If you don't want to execute that, you have quote and then data inside. So all lists, in all lists, space is used as the only delimiter. So I have here function, and between function and argument, there must be a space. Space, space, space. Okay. So, and you have that this car encoder for having this address and decrement register, data register that they used here. So for sentimental purposes, these are head and tail of list car encoder. So if you have this list 1, 2, 3, 4, if you say, give me car of that, you are going to get 1, which is head of list. Give me CUDA, this is 2, 3, 4, it is tail of list. So car encoder decompose list into head and tail. Now, you know from Prolog what you can do when you decompose list into head and tail. What can be done? Everything. Everything that you want to do can be done by decomposing head and tail. However, in functional programming, this is much more powerful because these objects can be whatever you want. This can be numbers, but can be heterogeneous objects and can be functions. So I can have here 1 function, 2nd function, 3rd function, 4th function, and I can combine them any way I want. So this gives you unbelievable freedom to do acrobatics with functions that has very useful consequences. There are anonymous functions. You can say lambda of n is n times n. So this is function without name. And you have to put here something to say that it is without name, so all of them are called lambda. But there is no way to name them unless you say define f, and this is going to be lambda function. So this expression here is a pure operator. So operator of a single operand, and you have that what is performed is multiplication n times n. Multiply n, n. Okay, so you have that all operators are given with operands in the list, operator, and then operand, 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 any number of them. So that's what we did. We said lambda of n is n times n. So this is function definition. And then this function is applied to argument f. So it returns the value 25. This is return value after you apply this anonymous function to this argument 5. Scheme was invented by these 2 guys, Guy Steele and Gerald Sussman in 1975. And then it was standardized and redefined many times. It is used in industry and commercial applications. By the way, you all know Unix. Okay, now you have that most of Unix products are written actually in Scheme, like Emacs. Emacs is written in functional language inside. Okay, so Lisp and Scheme are used for software development, and you can go to internet and find plenty of success stories, industrial success stories based on Scheme. So these two guys are still very active and alive. And their idea, number one, was to define the first class objects. Now, in the case of Prolog, the fundamental concept of Prolog is what? Flexibility. Flexibility and pattern matching as fundamental mechanism that gives you possibility for interchangeability of inputs and outputs. And this is fundamental truth of the logic programming. Now, what is the fundamental central concept of functional programming? It is the first class object. The first class object is object that must satisfy these conditions written in blue here. First, may be expressed as an anonymous literal value. So anonymous literal value represents itself. This is a constant. So if I say number 3, it represents itself, it doesn't have name, and it is anonymous, nameless, literal value. Literal value means it represents itself. So this is the case with numbers, real integers, with characters, and in Scheme, this is also a function. So function can be expressed as anonymous literal object, like this lambda expression. This is a function without name. Objects must be storable in variables. So if the object may be stored in variable, this is the first class object. May be stored in data structures. So you can put that in a list. You can put such objects in a matrix, in array, in whatever you want. May be comparable to other objects for equality. Well, this is a big thing. If you can compare two lists for equality with each other, and this list can have complex structure inside and be either proper list or trees or whatever you want, comparability of objects for equality does not exist in C or C++. I cannot say if array A equals array B, do something. God forbid, you have to write a for loop and ask whether A1 equals B1, whether A2 equals B2. You have to instantiate the counter, you have to increment the counter, you have to go through this from the beginning to the end. You have to write a function, practically. If the language gives you comparability of all objects for equality, so if you say in object A is equal object B, this should work for objects that are huge, that can have inside any kind of structure. So this is something that is very important. Maybe pass as parameters to procedure functions. So you can pass that object as a parameter to any function and maybe return as a result from procedure function. So you can, in C, for example, you can return from function an integer or character or real number or a pointer to something, but you cannot return object itself of any complexity. And of course, you cannot return function. You can just return numerical values. Maybe dynamically created, destroyed at runtime. So there must be the possibility to create a new copy of that object right in the middle of computation, and there should be possibility to delete it in the middle of computation. Look at this. Must be readable and printable. That means object of any complexity must be readable, which means if you have read statement that is reading something from keyboard, this cannot be stupid scanner that is going and giving you a string of characters, which is completely useless unless you have something else inside that is processing that. If you have that object is printable and readable, that means that you have the complete lexical and syntax analyzer that is analyzing that object at the moment of reading it and deciding, is this a legitimate object of the language, including any degree of complexity. So this is very difficult condition to satisfy. That must be readable and printable. But sorry, if you are first class, you are printable. So if you have any object of any complexity, it must be printable. And that's what Ruby is trying to do. There is one kernel function that is called P, just P. And if you say P, and after that object, you get the object in human readable form. So that is an attempt to come close to first-class languages. It has intrinsic identity independent on the given name. You can give any kind of name. Maybe stored outside running processes. That means you can store it on disk and read it from disk. Maybe transmit it among processes. If you have two processes that run in parallel and you put pipe between them, you can push object through that pipe from one running process to another running process. You did that in 4.15. So now these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 difficult conditions. So objects can be used without restrictions, have anonymous values, can be stored in variables, stored in data structures, readable and printable. In Scheme, all objects, including functions, are first class. It is fully first class language. All this is satisfied in Scheme. You can do any of these things. So elimination of restrictions contributes to expressive power of language. Expressive power of language is the capability of language to create easy and unrestricted programming solutions. This is not something that you have in C++. C++ has gazillion of restrictions, including if you want to display something, you can display character, you can display string, you can display a real number, you can display integer, but nothing more. For everything else, you have to go home and write your own software, which is overloading inserters so that you can insert an object in the output stream. This is not going to work for anything except for these 4 or 5 basic data types, for nothing else. So this is not the reason not to use C++. Of course, we use it in industry day and night, and it is going to live for many, many years in the future. But it is good to have first-class objects and first-class languages. And this is what we are going to take away from our study of functional programming. Languages that satisfy all these conditions that are first-class languages. So the first sentence in the Scheme language standard is written: programming languages should be designed not by piling feature on top of feature, but by removing the weaknesses and restrictions that make additional features appear necessary. So this is something that is a very explicitly written concept that is making difference between big languages and small languages. So the goals are simplicity, generality, small number of powerful fundamental concepts. And of course, there are standards. And there is this revised report on the algorithmic language scheme. I posted one of them from 1995, and there are newer versions on iLearn. So you can go there to read that. And this starts by this sentence. That's the sentence that is taken from that standard. Scheme implementations. There are multiple free implementations that are available. First, you have MIT and GNU versions of Scheme. You can use them if you want. The version that is used for writing this reader at the time when I joined the university, San Francisco State University, is made by Texas Instruments. This is a nice and powerful scheme, and it has a nice manual, except that it works only for 32-bit machines. It is old in 1988 or something like that. And at that time, machines had 32-bit word, no more than that. And so you can download that from iLearn. You can install it on your machine, provided that you have a 32-bit machine. And this is how the reader was written. So you still have programs that run with Texas Instruments scheme, but you cannot run that on 64-bit architecture. University of Geneva had one beautiful scheme that was made by Texas Instruments for them. And then Racket, called also PLT scheme, which is dialect of Lisp and expanded descendant of scheme. So here is an example of Texas Instruments scheme. It looks like this. You can do whatever you want with that to define, for example, this caret here to be lambda of n, which is n times n. So now you can map this caret to list that has 1, 2, 3, 4, 5. That means you map quadratic function to list of arguments by mapping this function to first argument, second argument, set. And so what you get is the list of squares. So if you want to process this list of arguments with square function, it is going to be applied to each of them, and you're going to get back the list of squares. You can also apply this square of square of square of square, and you get huge number, and so on and so forth. So 3 square plus 4 square, square root is 5. Exit will bring you back to the operating system. Same works with Racket. Okay, there is also an important book, How to Design Programs, that is based on scheme. This is this introduction to computing and programming by these 4 people. And these are key people that are developing the Racket operating system. You can also have this Dr. Racket, which is the same as old Dr. Scheme. You have 2 windows here. In this window, you keep the definition of functions, and here you can execute them. And you can have run and do variety of other things with that. You can also save programs, develop programs, load programs, whatever you want. So here is square lambda of n, which is n times n, or quad, which is lambda of n that applies square of n. Why square of square? Because everything that you define can be reused later and have that now you apply square function of this argument n. And this is called quad. Now, here is quad of 2. Quad of 2 is 16, or quad of 2, 65,000. Or square of 32 is 1024. And you can have lists that you can make with operator list, or addition of arguments like in this case. So you can here execute, here you define functions, and then whatever is defined here you can use here, which is usual way of 2-window IDE for development. You can develop here something and here use it. For example, here is a weighted power mean, a function that can be geometric mean or arithmetic or quadratic or harmonic. So I define this as a function that works weighted power mean with exponent r. So if I put this exponent, which is r, to be 0, then this becomes geometric mean. Otherwise, this becomes arithmetic mean, quadratic or harmonic. And then you can here execute them and see the values that come as a result. So you have lambda expression, but inside it, you can have other lambda expressions. And this makes magic, that you have lambda inside lambda, and you can combine functions that are creating variety of things. We are going to do that later. There is also MIS scheme, which is currently called Racket. So the window that I showed you before was this Racket here. And these are same examples that you've seen a minute ago. So if you say divide 1 and 3, you get this 3, 3, 3. So this is currently called Racket. And when you click to Racket, you get this environment that has, as you see here, interpreter. So it is interpreter because you have here an expression, click return, it gives you the result. So it works that way. Documentation, go to racketlanguage.org and you have plenty of things that you can download, quick reference, guide, this book, how to return design program, etc. So we are going to avoid reading this except this slide because we have nesting of functions in functional programming. So you can have this function of these arguments that returns a value. And then this is one component in another function that returns value. And this other function is component in another function. So you have function, inside function, inside function, inside function. And then you get the result. So functions should not make other effects other than returning value. So the only purpose of a function is to return the value. Value can be any argument, any object of any complexity, including another function, but no side effects, because it is difficult to control if you have various side effects. So scheme uses a small number of powerful basic concepts. It is has simple syntax based on lists. Everything is first class. It has easy recursive programs based on tail recursion, nested functions. Each control structure returns a value. There are no side effects. It is using anonymous functions. It uses functions that have arbitrary number of arguments. That is something that is important, and you're going to see that also in Ruby. Arguments can be mandatory, optional, or missing. Functions can be composed using multiple levels of composition, so you can have lambda inside lambda. And functions can be returned from expressions and from other functions. Now, one thing that we might like to see, if we have it here, we don't have it here. Let me try to find this. I would like to see give me a second to find that stuff, and 600, and let us go to scheme lectures. They're here, and let me put it on the screen. So to share to share this screen here. Okay, so this is something that I can put to here, and maybe to make it a little bigger, like this. So this is the reader, and we can go through these slides of the reader, and we covered all of them. And the first thing that you have in the scheme is the scheme reference card. So we started with the scheme reference card, and unfortunately, there is no scheme reference card on the single page, because scheme is a rather big monster. And It is a small language, but still has all these features that are listed here. So I want you to go with me shortly and to see what does exist inside. So the first thing, I want to give you a survey of this language, and I want you to see what is going to happen because you have to learn these things. So we first have a group of arithmetic operators and functions. So we have that you can have operand and then operator, operate. For example, addition of various expressions, and you will get addition, subtraction. There is increment operator called add one, but you can also write one plus on some languages. So there are some differences between these languages, and you're going to see that works in Texas Instruments, something doesn't work in Racket, etc. So be tolerant when things like that happen. You don't have that everything should always work. Something will, basic things, of course, are standard and work everywhere. But these little things like one plus, is this working or not? Don't be sensitive. It is not working in one version that you have. There is always a way how to do that. So multiplication is multiplying objects. This is division. Exponent, expt, is the power function. So this is based to exponent. So it has two arguments. For example, exponent of 2 and 3 is 2 to 3, which is 8. Float is converted to float. There is pi, same as in Prolog. You are going to see that many things in Prolog are stolen from Scheme. You are going to see them soon. Then you can have quotient, integer division, remainder, ceiling, floor, rounding, truncating, modulo operation, greatest common divisor, least common measure, multiple. You have all of them as these basic arithmetic operations. Then you have library functions, like in each language: absolute value, square root, maximum, minimum. Maximum and minimum are working, not surprisingly, with arbitrary number of arguments. So you can have any number of arguments and you can deal with that. Then you have exponent, exponential function, logarithm, sine, cosine, tangent, arcus tangent, arcus cotangent, arcus tangent here. So all trigonometric functions, and their inverse functions. Then we have 6 relational operators: greater than, less than, greater than or equal to. All of them have 2 expressions and return true or false. So if you have whether something is greater than or less than an object, so you can go here. If we still can do that for a second, we go here and say, what's going to happen if I ask whether 1 is greater than 2? Okay, false. So you have pound f, this is false. Okay, but if I ask if 10 is greater than 2, I'm going to get true. So you have Boolean values, and Boolean values are same in all languages. So you have this possibility. Where are we now? Here. Okay. So you have possibility to have relational operators. Then you have recognizers. You can recognize whether an object is a number, Boolean, character, string, symbol, list, integer, float, real. Is it atom? Is it pair? Is it rational? It is end-of-file object. This is necessary for processing files. Okay. Is it vector? Is it procedure? Then we have tests, whether something is 0 or positive, negative, even, odd. Then equivalence predicates, EQ, equal, and EQE. You remember those literal equality, which is pointer equivalence in Prolog. Well, this is stolen from here. This is one of equivalence predicates. Then we have Boolean functions. We have characters and all possible operations with characters. For example, you can have the possibility to ask whether a character is alphabetic, is it numeric, it is white space, uppercase, lowercase. You can convert character to integer and integer to character. This minus greater is an arrow. So character to integer, you can convert, and you can integer to character convert. Strings. Strings exist, of course, and plenty of operations with them. Look, from here to here are all string operations, variety of string operations. Of course, you can process string in variety of ways. You can convert string to list, list to string, and variety of other things, substrings, etc. So this is all available. Pairs and lists, you have pair is, of course, a pair of objects. It is how to make trees. Pairs and lists are the study of trees. Then we have vectors. Vectors same as array in C or C++. Then we have various definitions and binding. Define variable, define a function, define whatever you want. It can be defined recursively, not recursively. Functions, not surprisingly, lambda, define functions with name, define, etc., variety of things. Then comes the full set of control structures. If then else, condition, which is generalized if then else, case, statement, all that is available. And then after that, loop, do loop, one ugly loop that exists in scheme that is looping from initial value to the final value. And then you have to ask the question, what is going to be returned now? Because each control structure must return something. And if returns one of two values, and do is also returning a value. Then you have input-output. And input-output has variety of things. And then display, for example, is displaying. Read is reading from input port. So it has concept of input port and output port. You read from input port, write to output port. What are these ports? Well, they can be keyboard and screen, but they can also be files. So you can read from file and write to file, and this is completely legitimate thing to do. And then here we have a gazillion of scheme transcripts that show how to use scheme, and this is what we are going to study next time. So that's the reader that we are going to study. I have to also let you know that you should now have this installed. So please go to racket.language.org and download Racket. It is, I installed it yesterday on this machine. This new machine doesn't have anything on it. So I had to install it, and it is currently is version 7.8. And this version 7.8 has, I think if I remember, 79 megabytes. It is not too big. So you need 2-3 minutes to download that, and then it is self-extracting, executable. It is going to install everything, and in particular, it is going to give you two things: Dr. Racket, which is this two-window environment, and Racket, which is just interpreter that we used a minute ago. And I suppose you are going to have that without problems, and you can use it. Of course, as always, start to work with that right now, right today, and play with this toy. It is a nice toy. You're going to have plenty of fun playing with it. So use this opportunity. Now is the time to learn functional programming. Any
Professor?
question? Yes, sir.
So when we load up Dr. Racket, it asks us to select the language. Do we choose the student one or the Racket lang?
Users say language Racket.
Okay.
If you put student version, that's okay. I use that student version without finding what is the problem with it. Pay attention. That's a good question. Racket is not just this scheme that I showed you, but they put gazillion of junk on top of it, you know. They have a complete interface with other languages. They have complete graphics, for example, on top of it. Then recently they introduced inside some other things that has nothing to do with this. They have for loop, for example. This is nasty. Okay, why to have for loop when you have head and tail? But it is much more than it is here. So these other versions of language are expanded version. We are going to stay within scheme part of Racket. Well, I'm not interested in Racket as a language unless we have another course that would be language-oriented programming. Then Racket would be the main vehicle for doing that. But at this moment, we are not going to do that, and it is going to stay inside the frame of scheme.